Okay, so thank you all for joining us this morning, afternoon, or evening, depending on where you are in real space these days. Um, my name is Cory Czarnik. I'm the product manager for imaging and in situ products here at Gatan. Also joining me is Ben Miller, who is an application scientist in the group as well. And so between the two of us, I'll go through the presentation and then we're happy to take your questions. Just please type them in the pane, the question pane, and we will either answer them in real time, Ben may answer, or we can talk about them at the end. Okay. And with that, we'll launch into the tutorial for, didn't read the title, Developing Comprehensive In Situ Workflow for TEM Experiments. So different people have different ideas of what an in situ experiment is and what the ideal workflow is. So this isn't intended to be a product specific pitch. It's more talking about the ecosystem that Gatan has developed to integrate tools and integrate in situ functionality for those tools into GMS and digital micrograph. So here you can see just in situ, most of you are familiar with, can be various different dynamic events that could be happening, mechanical, electrical, it could be light, heat, gas. These are some of the more common ones. It could be even, to a certain extent, we consider continuous tomography in situ because you're tilting around. But all the products shown on the right have in situ flavors or in situ aspects or capabilities associated with them. So they all can be time resolved. This could be time resolved just bright field image. It could be EELs. It could be 4D STEM. I'll give you examples of those as we go through the presentation. And just as a note, so we do have, I know Anna's talking about the Stella camera quite a bit this week. So I would defer any questions about that specifically to her. So historically speaking, there have been multiple PCs required to perform a single successful in situ experiment. And these got really complicated. Even if you go back just a year or two or three, you had to coordinate data coming from different PCs. So here you have the TEM PC, which controlled the microscope, a PC for the camera or other primary detector. You could have a PC for the EDS detector. This could be a holder PC as well. Or you could have 4 PCs if you had a holder in here as well and you were doing a heating experiment, for example. So having to synchronize these and then go back and reconstitute the integrated in situ data is a formidable task, to say the least. So you might get, diffraction, bright field, high-res imaging from the camera. You want to see what that looks like with EDS or a particular holder. And this increases the cost, it decreases the productivity. And as I mentioned, you have to coordinate data between different PCs, which is frustrating and fraught with potential complications because all the sampling rates will have different frequencies. So some may be, single hertz, some may be tens of hertz, kilohertz. And so you have to figure out how to combine all that. So it's clear that the in situ TM experiments are growing in terms of their use, applications, diversity. Our mantra is, one, don't drop any data. But two, we would like to be able to keep all the collected data and metadata in a single location, because then you can query, longer term, you can query based on different experiments, different parts of the experiment. You can see what's happening in terms of temperature of the sample, or you can look at images or other data that's coming from it, and you can reconcile that with TEM status information that you might be pulling from the microscope. So the challenge is that, ironically, people for a long time said, well, we don't have the ability to collect the data that we want, and so there's nothing we can do. Well, now we've removed that particular obstacle, And we see what the next, peeling the onion, what's the next problem? So the next problem is we have a lot of data is now routine. Like it's quite simple to go into a lab that's equipped with one of these high-speed cameras, for instance, and generate hundreds of gigabytes, if not a terabyte of data. It's you can have a couple terabytes in one day. The biggest two issues are how long it takes to get to the desired result. And we'll talk about that. That goes into the workflow. And the second is, how do you manage these large disparate data sets? Often from different sources. I mentioned they have different sampling frequencies. So that's a challenge which doesn't really have anything to do with the science, but it's sort of overhead associated with conducting the experiment that you really want to minimize as much as possible, so you can get to the science, you can get to the result. So the opportunity that Gatan's trying to expand is minimize or eliminate the copying and the alignment the data set alignment you need between multiple PCs. So if you have one master that reconciles the data, provides it to the user, that's going to be the most efficient and the most streamlined. If you have hundreds of gigabytes, just simply copying that can take some time, depending on what your bandwidth is and what you're trying to copy it across, what network. Reduce storage requirements. It may sound like 50 terabytes is a lot of storage, a lot of hard drive storage. And I forget who the talk was for M&M this year. It might have been Dave Mueller, said that they just purchased 50 terabytes of hard drives for a few $1,000s, several $1,000s maybe. But that is not a long-term solution. That's like short to medium term. So what do we do to increase the efficiency of the data that we're collecting, going towards the desired results? And the other thing is we want to eliminate multiple copies. It doesn't make sense to have 2 or 3 copies of the exact same data residing on, for example, my laptop and on the TEM PC and on some server somewhere. So you really want to store it once and be done with it. So GMS, to a large extent, can act as the hub of an entire experiment today. The largest volume of data typically is the imaging, or it could be the STEM, right? These are two-dimensional images that you have to acquire and store. They can be single bit depth. They could be 12, 14, 16-bit depth. And so if you do that, say 100 or 1,000 or 10,000 times a second, the total storage requirements adds up pretty quickly. And that's just the two-dimensional data. And so you could talk about three-dimensional data. You could talk about four-dimensional data like we do for STEM. We could talk about five-dimensional data. We could talk about STEM with a time axis in there. So you have all the tools today. The typical microscopist, in-situ microscopist, has all the tools they need to run these experiments. It's more a question of how do you herd them and bring them to bear and make them the most efficient. So just looking at cameras, if you look to see it, what happened to the explosion in data rates, this chart I think shows it pretty well. You'll note that the y-axis is in megapixels per second output of the various cameras, and it's a log scale. And then the particular year is on the X scale. The biggest change, and of course there's a hockey stick as we move to the K2, K3, but all of the CMOS cameras are orders of magnitude higher than what we were dealing with in the past with the Langshan or ICE and Ultrascan, which were typical for CCD-based cameras. A couple reasons for this. One is because the industry is moving to CMOS-based chips, in most cases proprietary chips, proprietary designs. The CMOS chips have pixel-based analog digital converters, and so you don't have, for example, a single read port for an entire 4K by 4K CCD array. And we can take advantage of multiple columns of readouts. And so we parallel process the image to increase the data rate. The other big improvement is in the high-speed data handling and sort of what I call off-the-shelf networking and, for example, 10 gig capabilities, InfiniBand, There's other things in other communications protocol internal to the cameras that we move a lot of data around really, really quickly. And we're really pushing the limit of what is commercially available today. And we expect to be here for some time. But we can support the data rates that you see posted today at Gatan, including K2 and K3. One other note here, you see up on the right-hand side, K2IS was, set a new benchmark for the output of megapixels of a camera per year. And this bifurcation between output and stored reflects our philosophy going forward with K3 and, for example, K3IS. The camera is very capable of running super fast, but we don't necessarily want to store each individual image because, as some of you may know, a counted image by itself is not particularly interesting. And so we sum them, and we only save a sum of a handful of frames. And that reduces the total output and reduces the total data requirement. And so I expect that the total data rate may flatline. We'll probably go up somewhat, but I don't see another 3 orders of magnitude increase in the next 10 years. Traditional workflows, as I mentioned at the top, you might have one PC, you might have a couple different PCs. The first step is set up the microscope, set up your experiment, get everything exactly the way you want. Make sure your sample's good. Make sure you've got a good area of the sample. Your focus is good. Stigmation's good. Everything's set up. Then you execute the in-situ experiment, and you go ahead and collect data. And so the holder, for example, will be collecting temperature, set point, and actual data, ramp rates, things like that. The Gatan PC would acquire everything that it's plugged into, and the TEM PC is managing what happens in the column. Then you have to transfer all this data and reconcile it, as I mentioned, somewhere. And so this could be on the Gatan PC, it could be a third-party offline storage RAID array. Many people do, but that takes time. And if it's a lot of data, it's going to take a lot of time just to transfer it, much less the additional storage requirements, support requirements, redundancy requirements that entails. Then you can take advantage. You don't have to necessarily use the TEM Gatan PC for analysis. You can attach a post-collection PC to do the analysis, but then that also takes some time, right? You have to reconcile the data. You got to line up the disparate data types on the time axis and try to figure out what it all means. And then you come to some conclusion. Maybe it's great. Maybe you're on the wrong area of the sample. Maybe you were expecting something different. Maybe you want to repeat it. So then you kind of have to go back to the beginning. And if your experiment's not repeatable, like if you're doing a melt quench experiment, then you're probably okay. But if you're doing a mechanical deformation experiment, then you need to make a whole new sample, or hopefully you have more samples. And so the cycle time becomes pretty onerous with those iterations. So it could be minutes to run the next iteration. It could be hours, or it could be days. Instead, what we propose is that you still may need a TEM PC for the column, because there are some things that some functions or some commands or some calibrations that can only be done through the dedicated PC. For example, the holders, the calibrations might have to be through there. The TEM, some commands. But you still have to set up the camera or the EELS, EDS, whatever you want to run on the Gatan PC. But then the Gatan PC should be able to collect all and align all of the various inputs, and you can execute the experiment directly from a single PC. Then these other sources feed the Gatan PC the data, and the user, in as much as the user can see in real time what's happening, has an opportunity to go back and make modifications on the fly. So they can, for example, try to keep an item of interest in the field of view. They may choose to change the focus or the Z height or something, right? Change the temperature, change anything. but that's based on real-time feedback of what they see. With the way we've architected our system, we can simultaneously transfer data to a remote location. And my colleague Ben had a real nice presentation. I'll revisit a couple of the slides he presented to talk about how you can do this with a remote server, and then so we can transfer in real time simultaneously to acquiring the data to a storage system, and then we can have an attached PC interrogate the data with a, it's hard to say it's truly instantaneous. It's not. There's some delay. It might be a second, fraction over a second, and then feed that information back to the user. So in this case, there's really only two steps, right? You have to set the thing up, and then you start collecting data, and all this is done on the fly. So you can imagine that this provides a lot more flexibility to the scientist who's collecting the data. You have a better chance of success, and you can make changes on the fly. So all those greens, so the blue steps are first, and the green steps is really where the interesting things happen and where there's a big opportunity to reduce the cycle time and the overall data requirements for storage. So here's a simplified, somewhat simplified, optimized workflow. So the items in blue here, step one, shown on the left in blue. The items in green that I talked about at a high level are shown in green. And I'm just going to kind of step through each of these for the rest of the presentation. So we'll talk about the first step first. So TEM control. If you, those of you familiar with Gatan, more recent GMS3 plus versions of digital micrograph are hopefully familiar with the interface. We do have significant control over the microscopes. You can see the little cartoon that we actually show in digital micrograph on the left-hand side. So you can see all the various detectors, the slit. You know, we can blank the beam, we can shut the gun valve, you know, EDS, scan coils, all that. We can raise and lower the screen. We can do all that through GMS. And storing, for example, the most simple is magnification. So storing the magnification is one of the more basic things that you want associated with your in-situ experiment. You probably won't change it during the experiment, but a month later, it would be nice just to know the details because you may have forgotten your firsthand experience. This is a laundry list, admittedly, but it's intended to demonstrate the variety of possibilities that GMS scripting offers today. So this is just a list from our documentation. And you see we have the ability to query, we can get information, we can change information, we can set stage, spot size, et cetera. And I'll go through a couple examples of this just to give you some real world experience. Since GMS also supports Python, we also have Python commands, which are analogous to this. So I'm not going to bother you with another list of Python commands, but if you go to the help in digital micrograph, you can go down to the Python section, you can get the list of commands there. And it should say script commands shown at right, not left. So some examples where GMS has to take control of the microscope. So continuous tomography. It could be, well, tomography. It could be continuous. It could be discrete. We can change tilt angles. You know, number of images. There is a 3D reconstruction required, which we don't have integrated yet. But we can supply all the data, and then you can apply your favorite reconstruction program to it. You can do things like montage. So this is a pretty impressive 8x8 montage with, I think it was 20% overlap. And so we have, you know, shift abilities, we have stage motion capabilities. And so we can demonstrate that we already have integration into the column command lines. And latitude. So those of you not familiar, latitude, it's a specific workflow. What's shown here is the sort of steps to acquire the results. You do a wide survey, you zoom in on grid square, you pick a location, then you select individual areas or crystals. And if you look here, and then you acquire the data shown in D, and then with your offline reconstruction, you can generate beautiful, nice 3D data sets. So this is all available today, right? This is just to give you confidence that we have much of the capability we need to do full-blown in situ experiments today. We have historically integrated not just Gatan holders, because Gatan is a very lovely assortment of holders, very popular, but also we recognize there's other unique capabilities out there that other companies are doing, like protochips and DEMS. We are working with both of those companies to integrate their holders, their solutions deeper into GMS. We have had DENS holder integration for some time. And so the in situ data we show you today, for example, in the bottom right, you see that we can display, this is an example of a temperature rise, fall experiment. And you get the images associated with that. And so you can actually query on the temperature map here, you can say, I want to see the image here, and it'll bring up the associated image. And so these two displays are linked in that sense. The idea is we want to collect all the metadata, as I said in my little workflow chart. It should all come through GMS, and then we can integrate it, and then we can provide the user what's close to a final snapshot of their experiment. Bright field images, just quickly, multiple we have, Rio camera, one view camera, K3 camera, they're all different. Some are just generate accumulated frames, although on a time axis shown on the left. On the right, you see counted examples, dendritic growth, and the timestamp. So, and note that it displays the accumulated dose rate, the timestamp. You have all of this at your fingertips. So constructing presentations and data summary results is quick too, because that is one of the expected outcomes from these experiments. 4D STEM, we have STEMX, which hopefully most of you have heard of. So this is the product we use to convert, quote, cameras into 4D pixelated, 2D pixelated STEM detectors. And they have very high frame rates, and so you can get really nice large area STEM images, and you can use virtual apertures, DPC, you can do strain calculations, and we can do all this because we can record this as a function of time. You can generate large data sets and see what happens under dynamic conditions. And example of just sort of parallel tomography with tomography. So it is possible. The cameras work great. The data is stored. It's integrated. So other kinds of detectors that have in situ capabilities, EELs and EDS. So we can map EELs and combine it with metadata in GMS today. There's 3 charts shown. The one in the upper right is an in situ plot showing copper and oxygen, and that is a movie, I think. There you go. It just takes a while to get started. So you can see how the valence state changes as a function of time. The bottom left is combining an EELs and EDS mapping capabilities into a single output. So this is combined with Python scripting. The lower right-hand side is EELs and 4D STEM. So this is an unusual combination because ordinarily you can imagine you can't actually do an EELs and 4D STEM experiment at the same time, because particularly for STEMX, the camera will consume the beam. So what we did in a clever setup was script something that alternated between collecting EELs data, EELs EDS data, and then would switch modes quickly and collect a 4D STEM map. And so you can generate this wealth of data in an automated manner. And you have the ability to script to do, change the variables, change the details, however you want to. So it's an extremely flexible system as well. So that's the blue step for step one. Step two is, I think, actually in many ways more interesting because it's about the data. So you're running an experiment, you're getting data. How do you know it's good data? What do you do with it? So the first step is you have to have a high-speed data architecture of your system, not just the detector and the PC, but how you process the data. Your PC has to be fast enough to deal with it. And this is something that a lot of companies struggle with for expanding and speeding up the data acquisition process. So key components are kind of what you would expect, but the reason I'm bringing it up is you have to balance these. And so you need a high performance CPU, but we aren't using, we're using sort of off the shelf commercial CPUs for this. And it handles most of the logic calculation capabilities, basic TEM, obviously the OS capability. It's a balance between the number of, well, we have to optimize the number of CPUs and the cores associated with it, the speed. And so that's when we specify a particular PC for a given product with Gatan, it either comes with the PC or we put the PC specs on the website. So customers have a choice. They can get the PC from Gatan, or if they need to buy that exact same configuration, because it is a highly tuned PC configuration for that product. Hard drives, the hard drives we supply can be tens of terabytes, but that really is only going to get you to the sort of medium term. So the same day you do experiments, maybe the same week you do experiments, but it's not a long-term solution. So we'll talk about that a little bit later. Solid state drives is what we use for the most part, particularly for the direct capture drives. We can include spinning drives, or you could have offline spinning drives just to get more terabytes for your dollar. So, and again, it's just a balance of price performance. The RAID configurations we can do today, we can increase the write speeds actually to keep up with the fastest cameras that we have today. So as I mentioned earlier, we can generate a lot of data really quickly and fill up hard drives. But that's not the yardstick. That's not success. Is generating 10 terabytes of data. And memory, so DRAM, stores real-time information. For example, if you're looking at Windows in GMS workspaces, you can load these PCs up with a terabyte or more of DRAM, depending on what you're doing. And again, it's relatively high performance DRAM. It is commercially available, so that reduces the price significantly. And if you want to load, for example, a multi-dimensional file, typically it would be loaded into RAM, so you can have quick access to it. So you need considerable amount of RAM on these as well. So this is just the infrastructure to give you the ability to store your results, really. You don't want to lose your results. The next question people typically ask is, well, what do I do to reduce the data size, the overall data size? I don't want 10 terabytes, I want 100 gigabytes. So what do I do? So there's 2 points where you can reduce the total data size of your experiment. The first is if you bin inline. So this is all inline. While you're either when you set up the experiment or while you're collecting the experiment, if you bin, you reduce the amount of data because you reduce the number of pixels that the camera has output, for example. You can use what we call lookback. So lookback is a buffer that is constantly storing the data that, for example, the camera sees, but it could be other detectors. And you can see something happen on the monitor and then start your recording, and you don't miss the data that is in the past. So you can put in 5 seconds, 10 seconds, 30 seconds. And when you start, it will actually attach the buffered data to the beginning of your stored data set, which is an extremely nice feature. You can just wait for something to happen and then you can hit record. And so your efficiency of filling up your hard drives goes up tremendously with this, because some experiments you don't know when things are going to happen or where they're going to happen. The user can define a frame rate, and so obviously lower frame rate, you're going to have less data. But depending on what you're doing, if you're running a very long in situ experiment, you may only want a data point or an image or a elemental map every second. And so we have this feature time lapse that lets you record sparse data. So your experiment might be an hour, and you don't want to fill up every single hard drive in the building just for your 1 hour experiment. So this lets the user determine the frequency and rate at which they save data. The other one is live FFT, which isn't directly related to data size, but because we provide a nice video-like frame rate for live FFTs, you can get a lot of information about your material samples just looking at the FFT. And many times that tells you if you're in a good area, bad area, you have the alignment you want, you don't, you're seeing the reaction you want, you aren't. So that's an extremely useful tool that a lot of people just maybe overlook. But that's our sort of primary line of defense, I would say. So you can either do inline or you can do post-processing. And post-processing, I'll walk through a detailed example, but it could be binning, cropping the images in time or space. We can sum or skip frames. So FFT, just quickly, most of you who do in situ experiments probably do this already. So in the top right, you see the real-time FFT. You see the dose count in the upper left, scale bar, and the timestamp. So we've accelerated this this particular playback. And you'll see here at the end that you've lost a lot of resolution. You lost a lot of information because this material is deforming under the electron beam. And if you start here, you can say, okay, well, we have this, but then at some point you aren't quite sure when this disappears and when this disappears. So you know when to stop the experiment because you know you're looking for a particular reflection. And you also have the ability to go back once you store all the data. You can pick a particular point in time and call that sort of the end of your experiment, depending on what you're looking for. So we can also crop in time and space, and we can sum and skip frames. So on the left, you see the full 4K by 4K field of view. And so here we have gold nanoparticles. So if we assume that we want to see the sintering event and the realignment of the particles as they merge, but we aren't sure when, and we aren't sure where that's going to happen because these particles sort of just float around. Once we record all the data, then we can go back and say, okay, here's the region of interest. This is the one I'm interested in. So we crop from a 4K down to this, which is a fraction of the full frame. And we can, see more detail. We also have the opportunity to bin at this point. We can change we can sum, we can skip frames, we can change the playback speed and create an MP4 video. We could even zoom in further if we just wanted to see the central region. And that's shown here. So we can crop it even further. And again, change the playback speed. So this is one of the primary tools if you're only interested in a particular region of a given in situ experiment. Next one is drift correction and tracking. So this is one of the early features we put into our what we call the IS player. And with this particle, you can imagine we're moving the sample around within the field of view artificially. But you can imagine this particle's just sort of drifting around your field of view. And if it went all over the field of view, you'd have to record the whole thing. But with the IS player, you can draw a box around this particle, and you can say track and crop to this particle and give me a new data set. And this is what the data set looks like. So not only is the particle of interest stationary in your newly created field of view, but the data size is also much lower because you don't need all the extraneous pixels and bits of information in your image. You can really focus on what is of interest to the experimentalist. So time to results. this is, the data volume can be overcome with brute force. You can always go buy more hard drives. But brute force doesn't work so well with optimizing the time to results and how quickly can you analyze data sets. If somebody hands you a hard drive of 5 terabytes of data, that can be pretty intimidating. So you may want to figure out, did I get the right data? Did I have the right sample in? Was I in the right part of the sample? Was the TEM set up right? Was data collection set up correct? And what conclusions do we need to extract from the experiment to design the follow-up experiment? Or maybe we're done and we're going to publish a paper somewhere, which is always exciting. GMS tools, which I'll show you some of, I've already alluded to the Python. GMS has multiple tools that let you quickly parse even very, very large data sets to let you sort through it and figure out really what do you care about and what was expected and what was unexpected. And so I'll give you some examples of those. And Python, hopefully people are familiar with Python. We have Python support. Py40stem is a popular 40stem analysis routine within Python. So you can also create movies, which is nice. So you don't have to worry about screen captures. We can create MP4s, which is everything that you're seeing here. And you can do so with all of the capabilities of the IS player I talked about. So this is an interesting experiment because here you see the diffraction pattern, and we're recording this in real time. So this is a very large image. And here's the arbitrary intensity. If you look at a radial summation around the pattern, the y-axis here is in time. So this is time 0, and this is as you increase, as you go on in time. And this is just looking at the angle in the map. So there are some things you can do real time. So we could construct this map in real time. And post-processing, of course, you can get into details and do complicated analyses, but you can at least get a sense of what's happening with your experiment with this. The other nice thing is that the amount of data that's generated by the system is extremely high, but what you have to query and analyze can be very small. So this is one of the tricks is, you may generate hundreds of gigabytes or terabytes of data, but if you focus on the things you care about, you can do so pretty quickly and get results back to the user sitting at the microscope in a short period of time. So this is just giving you a visual comparison of the full data set. And if you just took 20% of the frames and you said, I'm just going to plot 20% of the frames, they look pretty similar. You'd be hard pressed to differentiate between the two of them. And if you could analyze a significant fraction, but say once a second or 1 out of every 5 frames, and provide that feedback to the user, that would be extremely helpful. So this is just an example of something you could do, because while you see little difference between the data set as it increases in time, if you take an average of this and then subtract that from the data set, you can actually see where things change, right? So this is the start of the experiment, and this is about the point when things start getting interesting. And then the rest of this, it all stays fairly common. So you can get, if you're sitting at the microscope, you can get this kind of feedback in, again, not instantaneous time, but very, very quick, real, I would say real time. You can imagine other things. So this is a clever experiment Ben did. If we collect this diffraction data, but we're only interested in a particular spacing. So we only care about reflections that appear, in this annulus. So we can actually filter that. We can say, okay, anything that has a dot above some critical intensity, I'm going to record that image. And the rest of them I don't care about because it doesn't have what I'm interested in. So with that, if I play this again, you can see the images match and everything in between, right? We aren't bothered with all of the non-data of interest. which is an extremely useful. Again, it's time to results. You don't have to watch all the video. You just have to watch the video that is in the filtered analysis. So this is the part. This is the part where I explain the power of the IS player. So we have this tool that's on the right. It is modified. If you're looking at a GMS version that's maybe a year old, we are tweaking this. And you see it's got a lot of functionality. We can modify space, we can modify time, we can process the data, we can export the data. And I just want to walk you through this. And I won't give you examples of all of them, but we can crop ROI in space. So we can crop the extent or the size of the image. We can crop the resolution of the image. If we go to higher binnings, you lose resolution, but your data gets smaller and you generally increase signal noise. We can crop time. And so if we took 2 minutes of data and we only care about 10 seconds, you can only save in post-processing, you can only save the 10 seconds you care about. We can also change the resolution in post-processing. So we can combine frames. So we lose some time resolution, but we get more signal because we're combining the signal from adjacent frames. We can filter. And we can filter the full frame, we can filter an ROI, we can drift correct, we can track particles. So lots of capabilities built into this, and you can mix and match. So you can decide you want to crop in time and bin in space, or you want to do drift correction and crop in space and combine frames or skip frames. So yeah, it's an extremely powerful tool. And this is probably the single largest feature of digital micrograph that lets you get directly to the results that you want. Just as an example of this, if you have a K3 data set that's 150 frames a second, so you see that the field of view for pixels, each frame is 23 megabytes, which by itself isn't big, but you get a lot of them, and 1 minute's 200 gigabytes. Which 1 minute's certainly not inconceivable. So 5 minutes is about a terabyte. But if you know what you're looking for, you can play the data back with the IS player and you can drastically reduce the size of the data. So if you crop to a 1K by 1K image because you're interested in a single particle, so you reduce the data by a factor of whatever that is, 20, say, something. You acquired the data at high mag, which you find out you really don't need or you don't care about, so you bin it by 2. So there's a factor of 4. We only care about 20 seconds instead of a minute, so there's a third of the data. We don't need 150 frames a second, we only need 30, and so we're going to sum frames and condense the information into a single output frame. And maybe we want to increase the bit depth because if we're summing images or something. So we can increase and decrease the total data size. But after all of this gymnastics, you see that we can take a very large data set and reduce it to something that's extremely manageable and quick, easy to share, easy to copy, easy to download. That's the intention of the IS player. So you can have strategic data reduction. You can capture as much data as you want to. We allow users to do that, but then we also allow them to very quickly follow up and just focus on what they care about. Drift correction I mentioned. Those of you familiar with K3 and counting may be familiar with this, but you can collect a series of images, a stack of images, and then the system post-acquisition can go in and cross-correlate these. You can use different filters, and you can look at the X and Y shifts, which are shown in the plot on the left. And this will align the images, and so eliminate the blur and increase the signal noise of the output images. I mentioned scripting a couple times. Why do we use this? Much software, including digital micrograph, is great for standard techniques, and we can offer vast capabilities that customers can use to mix and match. But there's always the next thing. And so to experiment, to try out new techniques, applications, analytical processes, that's to really test the boundaries, or if you want to tailor something. for your particular experimental design, or particular conclusions you want to reach. This is one of the main applications for scripting languages. And you can kind of do whatever you want to within the confines of the plugins that are available to GMS. But you can rapidly prototype, you can collect a data set, tweak it as you needed, go back, tweak it, go back, tweak it. It's a very quick development cycle time. Mentioned briefly long-term storage. We do supply tens of terabytes in the storage, but again, it's not a long-term solution. Some facilities or programs or research grants may require storing all data for X number of years. So that's something to consider when you set up your whole system. The inline data reduction is probably your best friend in this case, because you can optimize your experiment and your data acquisition so that you collect the data that you are most interested in, and you don't need the rest of it. Things like look back are extremely helpful for this. But in spite of that, at some point, whether it's 6 months, a year, 2 years, you will need you will need to expand the storage options. And there's no, so up until this point in the presentation, I've talked about effectively a monolithic solution. So GMS can provide most of the answers, not quite everything yet, the reconstruction, for example. But the local scenario, depending on the experience people have with large data sets and the resources at the site, vary depending if it's a national lab or a company or a university, and even within those universities vary wildly. So caveat emptor for your solution. But we have worked with, and we continue to work with, individual sites to figure out what works best for them. Just a couple options. You can get a scalable server. The example I said before, you go out and buy 50 terabytes of hard drives. Doesn't really cost that much, a few $1,000s, and it's expandable. But that doesn't really necessarily solve the backup of your data solution. It might not solve redundancy, right? If you lose a hard drive, do you have a backup copy? So there's still challenges remaining, even if you just every week go on Amazon and buy another 10 terabytes. You can do tape backup, which I think is historically been the default. It's cheap, it's slow, but it can be automated, and accessing the data depends on the system you have to a large extent. It isn't quite as simple as having the data on your hard drive or a server's hard drive that you can directly log into. So it's something to consider, but maybe that's long-term storage or long-term redundancy. So I mentioned this before at the top. So the priority not only is to not drop any data, not miss any data, but store all the data and metadata in one location. As we decrease the time scales, we collect a lot of data, but I've shown you that we have given the users tools to overcome the two biggest challenges: how long it takes to get to an answer, and what am I going to do with all of this data other than just stare at a hard drive and be intimidated by it. The opportunities, we've taken advantage of most of these. We continue to work on it and expand the capabilities of GMS. Reduce or eliminate the copying and alignment between the multiple PCs. I think we're well along that path, particularly integrating the holders. Reduce the total storage requirements, either through inline or post-processing, and eliminate the need for multiple copies, so you can more efficiently use the hard drive storage space that you have. So just in conclusion, GMS can act as the hub of these, of an entire experiment, because it can collect all the data, right? Most other data might be one-dimensional, might not be as high speed. And so that makes sense. Trying to move the imaging data around between another offline system would take a very long time relative to the temporal resolution that the experiments you're running require. So that's it. I know I went a little bit fast, but if you have any questions, or Ben, if you have any, we can entertain those, or people who are watching this on tape playback, feel free to email us with questions after the fact. Thank you very much. Ben?
Yeah, thanks. There was only one question that's come into the chat so far,
Okay.
and I answered it via chat
Okay.
about whether that radial summation of the diffraction pattern is built into GMS, which it's not at the
Right.
moment, but I can send the script. Actually, I was looking and found that the script to do that for FFTs is on our website.
That's good
But
stuff.
yeah, but to do it on a diffraction pattern is actually slightly trickier because the center is not necessarily the center of the
Right.
image. So it requires a different script, and that one's not online.
Yeah, but so it's a good question, and it's a good answer, because it demonstrates the point about, something you couldn't do or wouldn't have necessarily thought of in the past. You write a modest, I would say, script in Python, and you can get some wonderful quick analysis. And if it's something that the community needs and wants and uses, just like the live FFT is baked into digital micrograph, that's certainly something that we appreciate the feedback on. So. Okay, so if there are no other questions, Cory pauses for a second, then I will wrap this up. Thank you again for your time, and let us know if you have any questions after the fact. We'd be happy to talk to you. Thank you.